So, was able to solve a theory on this Div 3 contest. I'm not going to show the actual account in which I solved it. I transferred all of it to my main account. I have an alt account, but I'd like to keep that private um, because there are certain people that I know. That's just all I'm going to say. But yeah, I was able to solve a theory. I guess we'll quickly explain the solutions so that my video can get a lot of views because it's a new contest. And I didn't do so terrible where I can actually help people. And this is going to be quick solutions, by the way, because I only have 5 minutes. And but all the problems were um, all the problems from my theory were pretty standard. I just made some stupid implementation mistakes that cost me some time, and I got no penalties though, which is fine. So for problem A, I'm not going to read the question since I have to do quick solutions. Problem A is pretty basic. The idea is that I can just show you the code. Um, you sort the array, and if you're using Java, I don't just always use um, like a collections dot sort like this because you'll get hacked. I got hacked before like 3 times, so that's funny. But yeah, you basically sort the array. You keep 2 pointers, and then you keep 2 pointers at the end, and then you just like add them, right? So I think it's pretty basic. The reason why this works is because it's always optimal to color 2 elements. There's no point of coloring 3 elements because one of them is not going to be used, right? So I think that's pretty straightforward. Um, long. This one, I had a sus implementation on this one. Um, I don't think I'll get hacked. I don't know why I used a set. You don't really need to use a set, but the idea here for this problem is you notice that you can always get everything to be positive, and so just add the absolute value of all of them, and that's your sum. And then basically, um, you can get you can set contiguous blocks of negatives to positive, and then and if you just the number of contiguous blocks of non-negative integers will be your answer for the amount of minimum it takes. But there is an edge case. What if this contiguous block is zero, has all zeros? Well, then you don't have to actually apply any operation because the sign won't change. The way you do that, the way I did that, which is not needed, is I just added it to a set, and then I just check, okay, if the set size is not zero, if the first element is zero, and the set size is one, then we know that every element in that block was zero. Um, you don't really need to do this. In fact, you could have just checked, did you see a non-zero element in this block? In fact, that's probably better. I probably should have done that. I don't think I'll get hacked though because uh, n is 10 to the fifth. I'm not using any sus sorting. Should be fine. I'm only adding that many elements. Should be fine. Um, then we have C. So this one is a very troll question. Basically, I'll assume that you've already read the question. Basically, what you'll notice is just a basic pattern. Is that the numbers that are added, you start from n, and then you just keep dividing by 2, and you keep adding it. You can just see why this works. I don't really have a proof on this, but I think in terms of the contest, it's sufficient to just like you can, and it's because there's like binary trees are like like 2 to the power or something. So intuitively, you can just like divide by 2, and like 15 divide by 2, divide by 2, divide by 2, and it's like floor division too. So that's pretty basic. We got to do D. D is very basic tree DP. And it is DP technically, but basically you just need to find the amount of leaves that are below a node. And if it's a leaf, then you count it as 1. So we set all leaves to 1. And when we set all leaves to 1, we basically just DFS and then add a node. The amount of leaves below that node is basically go through every children and then just add the amount of leaves below their children, and that will be your answer. And then for a query, you just do a product. So pretty basic there. Then E was also pretty basic. Again, the reason I took a little bit longer than I should have is because I had some annoying binary search like equal statements. But again, binary search on the answer, it's pretty obvious that if 10 works, then 11 also works. So then when you binary search an answer, how do we check if it works? We just get the prefix sums of each segment, and we apply the queries for that binary for that answer we're trying. And if the number of ones, which we can get from prefix sums, is sufficient enough. If it's greater than zeros, return true, and that's it. Wait, I have more time? What? Okay. Well, if it's a so basically if it's more than the number of zeros, which can just be counted as length minus number of ones, then return true. So really, just binary search on the answer, and then you can use prefix sums on the number of ones up to a certain point, and then you can easily get the number of ones in a segment, and then that'll be enough to check if there's more than half of ones in that segment. If there's more ones than zeros, and that's pretty much it. So hopefully you did well in this contest, and I'll probably upsolve F1 and F2 as yeah. Okay.